ever wondered why dry fruits when soaked in water swell while raw fruits in salt water shrink? In either of these processes, there is a common factor. Can you tell me what it is? Well, there is flow of water either to or from the substance. Secondly, all the substances are membrane bound. Let's discuss the chemistry of these observations. First of all, we'll see what semi-permeable membranes are. These are membranes which allow the passage of small molecules like water. However, the passage of bigger solute molecules are hindered. Such membranes are called semi-permeable membranes. These membranes could be of natural or synthetic origin. The membranes found under the shell of an egg is an example of semi-permeable membrane which is of natural origin, whereas cellophane is of synthetic origin. Next, we'll discuss the phenomena of osmosis. See here, when a semi-permeable membrane is placed between the solvent and the solution, only the solvent molecules flow through the membrane. And the flow is from pure solvent to the solution. Or in other words, you can say, if semi-permeable membrane is placed between a dilute solution and a concentrated solution, the solvent molecules will flow from dilute solution to the concentrated solution. This process of flow of solvent is called osmosis. And this flow will continue till equilibrium is reached. That is, when the concentration is same at either side of the membrane. The flow of solvent from low concentration to high concentration can be stopped if some extra pressure is applied on the high concentration side of the solution. This excess pressure that must be applied to a solution to prevent the osmosis is called osmotic pressure of the solution. Osmotic pressure is a colligative property and it depends on the number of solute molecules and not on their identity. Next, we will see how osmotic pressure depends on the number of solute molecules. For dilute solutions, osmotic pressure is proportional to the molarity, that is C of the solution at a given temperature T. So you may write pi equals C into R into T. Here, R is a universal gas constant. If molarity is expressed in terms of ratio of number of moles of solute to the total volume of the solution, then you may write pi equals N2 by V into RT. Now, if you consider W2 grams of solute of molar mass M2 in the solution, then you may write pi equals W2 into RT divided by M2 into V. This equation may be rearranged so that you will be able to compute the molar mass of solute. This is widely used to determine the molar mass of proteins, polymers with poor solubility or even bimolecules which are not stable at higher temperatures. Now let us learn isotonic solutions. Consider two solutions of concentration C1 and C2. If the concentration C1 and C2 are same, then the osmotic pressure pi1 and pi2 will also be equal. Such solution having the same osmotic pressure at a given temperature are called isotonic solution. Thus, if isotonic solutions are separated by a semi-permeable membrane, no osmosis occurs between them. Next, let us see a practical implication of this. That is, the use of normal saline solutions for intravenous injections. Normal saline solutions has a concentration of 0.9% mass by volume sodium chloride solution. As the osmotic pressure associated with the fluid inside the blood cell is same as that of the normal saline solution, it is safe to inject it. Thus, if we place the cells in a solution containing 0.9% mass by volume sodium chloride solution, the cells remain intact. Such solutions are called isotonic solutions. On the other hand, if we place the cells in a solution containing more than 0.9% sodium chloride solution, the water will flow out of the cell and the cell will shrink. Such solutions are called hypertonic solutions. A yet another type of solution is called hypotonic solution. If we place the cells in a solution containing less than 0.9% mass by volume sodium chloride, water will flow into the cells and they would swell. Such a solution is called hypotonic solution. In fact, there are many examples of osmosis that you might come across every day. For example, the movement of water from soil into the plant roots and subsequently into the upper portion of the plant is partly due to osmosis. However, osmosis is not always useful. For instance, people taking a lot of salt or salty food experience water retention in tissue cells and intracellular spaces. This is because of osmosis. The result is an illness called edema. Finally, we may discuss reverse osmosis. The direction of osmosis can be reversed if we apply pressure larger than the osmotic pressure on the solution side. Now, pure solvent flows out of the solution through semi-permeable membrane and this phenomena is called reverse osmosis. A practical implication of reverse osmosis is in the desalination of seawater. As mentioned before, when pressure more than osmotic pressure is applied, pure water can be squeezed out of seawater. Here, porous cellulose acetate membranes are usually used. Cellulose acetate is permeable to water but impermeable to impurities and ions present in the seawater. With this video, we will wind up the discussion of determination of molecular weight from colligative properties. However, in certain cases, experimentally measured colligative property of a solution will be different from that of calculated theoretically by the laws of osmosis. Such solution is said to have abnormal colligative property, and that we will discuss in our next video. Now, we may summarize what we have learned today.
Manorama Horizon. Learning made simple.